Good morning, everyone, and welcome to section 5.3, which is about the standard normal distribution. So you'll recall last time we were talking about the normal distribution, which is this beautiful bell-shaped curve that you can see in my sketch. It's unimodal and symmetrical, with a mean mu that's right in the middle, and where the x-axis is our measurement x. And what we said last time, or in our last video, was that the probability that x is between values a and b is equal to the area under the curve between a and b. So a and b can be anywhere. Let's suppose that a is down here a little bit below the mean, and b is on the high side, and we were to calculate this shaded area here, then that shaded area is equal to the probability of x being between a and b. Now remember that the total area under the curve from negative infinity to positive infinity is equal to 1, so this shaded area will be some fraction of that, so it will be a number between 0 and 1. So a great question would be how to calculate this area. So how are we going to do it? For this version of the class, we're actually going to go ahead and use an online calculator. There are many out there. The one that I'm going to recommend is from the Hyperstat Online Statistics textbook at davidmlane.com. And I'll put a link in the description if I remember. The nice feature of this particular online calculator is it also does backwards areas, which we'll be using in section 5.4. So let's take a look at a screenshot for this online calculator and see what it is that we need. So here's a little screenshot here, and you can see that there's a bunch of boxes. The first thing I should mention is that we're using the default here, which is we're going to calculate an area from a value. And then in section 5.4, we're going to use the other one, the value from an area. And the input parameters that you have to put in, you have to put the mean in and the standard deviation. So let's make a couple of notes here. The first is that this is the default, that you're choosing an area from a value, and then you are going to input these values, the mean and the standard deviation. And then you have a bunch of choices for the relationship between your value x and what areas you want. You're going to choose one of these. And so for example here, it's showing what happens if your x value, which up in the diagram here is your value x, and then it shows you the area of the shaded region above x. And helpfully, when you click calculate or recalculate down at the bottom here, it changes the picture so that you can see the actual area that you shaded in. So I think that the best thing to do then, oh, and I should mention then that this box in the nice Primrose yellow here, this is your answer. So let's go ahead and do an example so we can see how this works. So here is our example. Suppose we know that the time it takes to commute between campuses, so Lansdowne and interurban, during rush hour is normally distributed. And we should highlight that because you have to know that it is normally distributed variable in order to use this table. And fortunately, from the student perspective, there's just not a lot of different ways that we can say this. I just generally say that it's normally distributed, so it's nice and obvious. And we've got a mean of 50 minutes and a standard deviation of 10 minutes. And our first question is, what is the probability that the next time you make this commute in rush hour that you will take over 65 minutes? So what we're looking at here is our x value, our data point of interest, is 65 minutes, and we want the probability above that. So if you make a couple of notes here, you would say that the mean is 50. You can write in the units if you want. It's 50 minutes. The standard deviation is 10 minutes. And because it says we want over 65, then what we're looking for here is that x is greater than 65, where x is our data point of interest. So if we draw this, we do a little sketch. Now, don't worry, I won't require sketches for test 3. This is just a helpful visualization to see what it is we're looking for. So I'm going to draw my nice bell-shaped curve. It's not totally symmetrical, but we'll just have to make it do. And here's 50, that's our mean. Let's try to make a nice legible 5 here. And it's not so important that your sketch be perfect here, but remember that one standard deviation is at these little inflection points, and so this, for example, would be 60. So there's 50, 60, and probably 70 is around here. And so 65, if you're making something look vaguely like the actual value you want, and we want over 65, so the shaded region that we want, it looks like this. Now we're going to use the online tool to calculate it, but we're just going to make a note that the probability we want is equal to this area. And we can see that the area is pretty small. So let's go ahead and look at our screenshot here. So once again, we chose the area value from an area, and we filled in our mean of 50 and our standard deviation of 10. And then we chose to put in that we wanted x above 65. And then if you take a look down at the bottom, it gives you the calculated area. And so we input, oh, can't spell input, what do you know? We input the mean and the standard deviation. We chose our x and the relationship we want above x, and then down here the area probability, this is our probability. So the probability that x is greater than 65 is equal to 0.0668, or if you prefer, you could write it as a percentage, which is 6.68%. And this is probably a bit more precision than the original question called for. So if you rounded that to either 6.7 or 7%, those would be okay as well. So let's just write that down also. Okay to round to 6.7% or 7%, because the question only gave 50 or 60, 50 minutes and 60 minutes, 65, so there's not a lot of precision. Okay, so let's do the second part. Part B, what is the probability that the next time you make this commute in rush hour, it will take you less than 65 minutes? So you could be really lazy, which is the way I'm going to do it initially. So you could do it in one of two ways. You could write, for example, you could say that the probability of x being less than 65 is equal to 1 minus the probability of x being greater than 65. Now I can already hear the objections. Just hold that thought for a second. I know that some of you are saying, well, what about x being exactly equal to 65? And we'll get there in a sec. But let's just complete this calculation first, and then I'll address it right at the end. So the probability of x being greater than 65 of what we just calculated, so 0.0668. And so you're going to get 0.9332, which is just 93%. Or if you prefer, you can actually just go back to our little online calculator. Here's our screenshot here. We've put in that we want the area from a value. We've again had our mean and standard deviation, and now we've chosen below 65, and you can see that the area that it gives is 0.9332, which is the same answer as above. Now, of course, there's a really great objection, which is what about the probability of x being exactly equal to 65? Which is the integer 65. Now remember that our variable x is a real number. So what we're saying is, what is the probability that x is equal to 65.000 with infinite precision, that no matter how close you measure it, it's really bang on and not even a little bit away. It's kind of like asking, what is the probability that the length of a stick is identically equal to pi? Not sort of like pi, not 3.14 and a bit, but really all the precision to an infinite number of decimal places. And so for variables that are real, they can take on an infinite number of values. So the probability of any one value is identically equal to 0. For real variables. The probability of any one value is 0. Okay, so let's take a look at part C. Part C is, what is the probability that the next time you make this commute in rush hour that will take between 45 and 55 minutes? So you could do something complicated, but we're just using our little online calculator, so I'm going to go and take a look at the screenshot. Again, we've chosen that we're using the area from a table. We're computing probabilities from other parameters. We've placed our mean and our standard deviation, and this time we've chosen the calculation between 45 and 55, and you can see that the area that it gives us is 0.3829, and so our probability is equal to 0.3829, or 38.29%, and I'm just going to do a little rounding here to 38%. So that's one example completed. Let's take a look at a slightly different thing, which is, what is the probability that a data point taken at random from a normal distribution is within A, 1 standard deviation of the mean, and B, 2 standard deviations of the mean? So let's just draw a little sketch here. And again, you won't be needing to do any sketching for the test. You can do a little sketch on some scrap paper if it's helpful for your visualization, and I really strongly encourage you to do that. But I know that some of you are using Word documents or just plain email or something like that, and sketching is a little bit difficult. So just make sure that you have the right sketch in your mind, and I won't require that you write it out. So let's take a look at part A. We are going to sketch this just so we can see what's going on. So if we're doing 1 standard deviation from the mean, then we're basically looking at from the lower inflection point to the upper inflection point, where here's our mean, and we're looking at this area here. Now, because we can have any mean, the easiest is to choose that our mean is 0. And then this is 1 standard deviation from the mean, and if you were actually plot this as z-scores, remember that a z is how many standard deviations away from the mean you are, then we're looking at between 1 and -1. So the nice thing here is that the online calculator, if you use a mean of 0 and a standard deviation of 1, then the value of x that we were putting in earlier is also equivalent to a z-score. So let's go ahead and take a look at some screenshots. I did both part A and part B here. Here's part A on the left. Here's part B on the right. So you can see that the area on the left, I chose area from a value with mean of 0 and standard deviation of 1. Then all these guys down here are z-scores, and the one that I'm interested in particular is between -1 and 1, and you can see that our area is equal to 0.6827. And then for 2 standard deviations, that's part B over on the right-hand side. Everything else is the same except that I've chosen between -2 and 2. You can see from the picture that really we have most of the area shaded in the first one and almost all of the area shaded in the second one. And looking at our results, the probability for part A, the probability of between, so -1 less than z less than 1 is equal to 0.6827 or 68%. And for part B, we've got the probability of being between -2 and 2. Standard deviations from the mean is equal to 0.9545 or 95.45%. And for students who are paying attention, oh look, it's the empirical rule. So if you're wondering where the empirical rule came from, it's basically talking about bell-shaped or mound-shaped curves. We said only around 68%. If we happen to know that it's not just mound-shaped, but is in fact a beautiful normal distribution, we can actually give more precision. We can say it's going to be 68.27%. And in fact, you can use other online tools to get more precision, more decimal places than that. But yeah, this is where the empirical rule comes from. So, 2 last thoughts. We said this previously, but I'll say it again. If you know the z-score of a value and want to compute probabilities related to that z-score, then use mean is equal to 0 and standard deviation of 1. Then the x value you're plugging in earlier is the z-score. And 2, when visualizing your answer, it can be helpful to use symmetry. And also the fact that the area under the curve, so this total area here, is equal to 1. And that means if you're going from the mean and you're only looking at the area of the top half, then the shaded area is equal to 0.5 or 1/2. And also, if you happen to know that the area above the curve, so just doing a little shading here, if you happen to know, for example, that this shaded area is equal to 0.4, then using the rule that the sum of the two have to equal 1, then the remaining region down here, this shaded area, is equal to 1 minus 0.4 is equal to 0.6. And that wraps up section 5.3.